Okay, hello NuPIC. Welcome to the NuPIC office hour for November 10th, 2014. Thanks for joining us. We've got Jeff Hawkins, Subutai, Chayton, Scott off to the right of your screen.
Yeah, you should come more.
Celeste. And yeah, Celeste in the background.
All right, Scott, you have to do more than just arms.
I don't think it would be there.
It doesn't matter, once you're next to the beer.
So,
Scott is growing a new beard.
Start going.
so first we'll take questions about Scott's facial hair at the end of the office hour. Okay, so we're going to take Q&A through the Hangout. So if you're on the Hangout, you should be able to ask questions here or through, or if you're watching, there should be some Q&A interface going on there. And I think some of you, oh, there we go. Now we're, oh, right. Hold on. Let me get rid of that.
Wow. Oh, no.
So we have a few people that have joined in.
God is growing a new beard.
So you guys, can you mute yourselves until I call on you to ask a question, please? And what I think we should do, since we have people live right now, is take the people that call, have them ask their questions, and see how Q&A accumulates, and then check the wiki and live. So I'm going to manually mute some of you guys. There we go. So let's start with Eric. Eric, can you guys see us and hear us okay?
Yeah.
Great. So do you have a question for us that you'd like us to address?
I don't know if you heard your question.
Maybe not. Is there anything you'd like to talk about, Eric, since you're connected?
Oh, yes. So recently, I don't know if you saw in the mailing list, I've been working on continuous HTM stuff. Like, it just basically is a formulation of HTM.
Go ahead.
Sorry, it's like I hear echoes, like, really delayed.
You sound good to us.
Let me mute my...
Hello? Okay. Now I can't hear anything.
That's okay. We can hear you, so go ahead and ask your question.
So do you have a question?
Go ahead and ask, Eric. We can hear you.
Do you hear me now?
Yes.
Oh, all right. So I was working on continuous hierarchical temporal memory, which I don't know if you've seen in the mailing list. And I've been using it for reinforcement learning stuff, because, I don't know, I'm just into reinforcement learning, which is basically motor control stuff. So what I've been doing is to generate the actions from the continuous, sorry, this is very confusing. I keep hearing like echoes from the past. It's really bizarre. So I generate actions by using one-step simulated annealing by seeing what the Q values are for the hierarchy. Sorry, it's so bizarre right now.
Take your headphones off and just talk, because we hear you fine.
Yeah, we can hear you just fine.
No, the thing is, though, I hear myself and previous things that you guys have said
Hey, take your headphones off.
over and over.
Take your headphones off and just use the microphone.
Yeah, but then I can't hear anything. I
Do
don't
you have two windows open?
Yeah, I don't know that the echo's coming from us. I had my microphone muted.
You can take your headphones off, say what you want to say, and then put them back on.
All right. Well, actually, I think I just found another window that was open. That would explain things.
Okay.
So now it works fine. So yeah, I'm trying to adapt it for my own motor control scheme. I haven't actually looked at how you guys are doing motor control, but I'm very interested in learning about that. But the way I was doing it is I added for each cell in a column, I added a weight, and then all these weights are multiplied by the cell states to get a Q value for a region. Q values for, in reinforcement learning, the quality of an action. So I can perform temporal difference updates by modifying these weights over time, and then I can perturb the inputs, which contain both the action and the sensors, to maximize this Q value. So my question is, the way I'm doing it right now is using one-step simulated annealing. Is this biologically possible in any way?
I don't know.
I've seen this thread, but I haven't been following it carefully. So has anyone else been following that thread carefully?
Not carefully. I saw your initial stuff, papers. I have not followed the latest stuff in detail at all. I mean, do you want to explain a little bit how we're doing sensory motor inference and learning? It's quite different. I think, from,
Well, I think you're ahead of us in some ways in this. We sort of dividing it down to two phases. One is sensory motor inference, which is really inference based on simple behaviors that are not being, they're not goal-oriented behaviors.
Oh, okay.
And that's what we think is going on in layer 4 cells. That basically it's saying, look, I find out what some other behavior is being generated, and layer 4 says, I'm going to try to make a predictive model and do inference on the object based on what somebody else is making a behavior change. Then that's step number 1. It's just, we think that's going on in layer 4 cells. And then the second step, which is how does the region of the cortex generate goal-oriented behaviors? That's step number 2. And as I've said in previous times, we have some pieces of that, but not all of it. So we're not doing the sort of reinforcement learning that you're talking about right now. That would be in our second phase. That would be layer 5 cells. Right now, we're not trying to learn behaviors. We're saying, given the system has some behaviors, which is true in the brain, by the way, the subcortical stuff has behaviors, and the cortex has to learn how to infer based on those behaviors. And then later it learns to control those behaviors. So I'm pretty certain that's what's going on. And we're just doing the first part, which is like the cortex saying, all right, some other part of the system is behaving, can I make inference from that? So if you're doing reinforcement learning and you're trying to do goal-oriented behavior, you're ahead of us, and we're not there. The second part of your question is why is it biologically possible to do simulated annealing in the biology? I guess I would need to know more about how that's working and how you envision it working in the biology.
Oh, actually, we have it working. So it does work. Like I've done mountain car with it, like solve the mountain car task. But the way it basically works is you treat it kind of like, I hate to use this word, deep neural net, where you give it the input and it outputs a Q value. And so what you want to do is find the actions that maximize the Q value at the current time step. So what I do is I use the prediction of the HTM from the previous step to predict what the action might be on this step, and then I do simulated annealing on that new action to get a higher Q-valued action. And but this only needs one step because it always memorizes what it has from previous steps due to the prediction. Yeah. So like build simulated annealing over time.
Is that going on continuously, or?
Yes, all continuously and online.
Well, I don't know if anyone else can comment on this. I don't know enough about it. I know a little bit about simulated annealing, but not a lot. And you know, I think the process in the brain is kind of complicated the way it works. We know, well, we know from biology that at any point in time, the cortex presents a set of options to some part of the brain called the basal ganglia. And the ganglia selects one of those actions and passes it back. So the basal ganglia is sort of your affective or emotional part of the brain. And so the cortex says, here's multiple things I can do at this point in time. And then subcortically, it's evaluated, and this information is passed back to the cortex and says, here's the one I want you to do. That's pretty well, at least it's the current neuroscience dogma. And there's a lot of evidence to support that. Now, how do I, at that level, I don't know how to map it into what you're doing in the simulated annealing. I just don't know enough about it to talk intelligently about it. Everyone else can talk intelligently about it. But we haven't been dealing with the problem you're dealing with yet. So you're out in front of us. You're a pioneer here. So, yeah, I don't know, but that's where we are. We're taking a little bit more, maybe too slow, but we're taking it more cautiously.
I mean, traditionally, what I know of simulated annealing is I don't know there's an analogous process in the brain. It's more sort of random exploration of a parameter space, and you know, you have this temperature parameter that you're cooling over time, and it's it's an optimization process. I don't know of any direct analog in the brain.
Well, I understood it as sort of the rate at which you settle is a variable in this case, right?
Yeah.
And so.
And then there's a random kind of perturbation.
Yeah, and you're on the more perturbations you do, and then as it gets, then you start settling in. You know what? It may be brilliant, and you may be right onto the answer, but I don't know.
I mean, I think whatever searching that goes on in the cortex, a lot of it's oriented towards novelty and explicitly trying out the things that you don't know, where you haven't tried certain actions before and things like that. So I don't think it's as random as simulated annealing. I think it's a little more direct.
Well, the other thing that most neuroscientists believe, again, doesn't mean we have to do it this way, but they believe there's sort of two different phases of learning. There's a phase where you're doing exploration, and you're sort of learning how the world works and what your behaviors do. And then there's a point where you actually have to make a decision to do something, and more of a goal-oriented behavior. And so learning in humans seems to be broken, at least people believe it's broken into these two sort of phases. So, I'm just sort of playing, I'm exploring, I'm figuring out what the options are, and then how the world works. And then another point in time you go, oh, I have to do something important, given my prior knowledge about that. I think that's general dogma of reinforcement learning as well, if I recall. But, I've been wanting to read your posts because there's been a lot of them. I personally have been very busy the last few weeks, so I haven't been keeping up with that stuff.
Oh, it's no problem.
Yeah, well, I like that. I'm saying my regret.
So thanks for your question, Eric, and I want to say thanks also for trying HTM alongside other machine learning techniques. I think that's interesting. It could fit into other places and other techniques. You're a pioneer. Congrats.
Thank you for having me.
It would be great to see sort of at some point more of a high-level description, like here's what I want, here's how the system behaves, doing some goal-oriented behavior or something like that, and make it a little bit easier. Because I jump into the threads right now, it's kind of like I have to go back and read a whole bunch of emails and see. It's not always so easy to do that. If you figure out.
This actually ties to Rick's question a little bit on the wiki. He wanted to talk about goal seeking.
Yeah, so
in general, so I don't know if
Rick
this covered it or not.
He's online right now, so let me unmute him and say hello to Rick from Australia.
We always say hello to Rick. He's always
Oh, I still have him muted somehow. You might have to unmute yourself. There you go.
Yeah, okay, you can hear me, yeah?
Yes.
Okay, so I watched the whiteboard session from the hackathon. Jeff was saying that for getting further ahead in the development of the sensory motor stuff and goal seeking, we need a clear problem statement. So what's meant by a clear problem statement? I just interpreted it myself to mean we need some sort of sample application. Back in the day of Zeta 1 algorithm, like 5 years ago, it was all very much driven by vision. So the clear problem statement was we need to get this vision sorted. Is that the way you're thinking about this? Yeah?
A little bit differently. I think the better example of a clear problem statement is that after the Zeta stuff, when we started doing the more biological approach here that we're very excited about now. We set about saying, we need to build a predictive temporal memory, and we had a set of attributes we needed the node had to perform. It had to be able to do online learning, it had to work with distributed memory, it had to be able to work with SDRs, it had to be able to do continuous prediction, it had to be able to do merging of sequences, it had to be able to do appending of sequences. We had a whole list of capabilities that we knew that the system had to solve. It wasn't even an application level, it was just a sort of a technical thing. And once you define the problem really, really well, then that is what's always worked for me, is to have a constrained problem that is the right one, and now you can almost always come up with the right solution. Vision itself is perhaps not clear enough. For example, one of the things we're working on right now is not just vision, but how it is that we form a stable representation as your eyes move. A stable and unique representation. So that's a pretty good defined problem. It's not solving all vision. It's saying, okay, I know that's true in the brain. I know we have to solve that particular component. that's going to get at the heart of much of what vision and time-based learning and vision is going to be about. So that's another example. That's what we're working on now. In terms of the sensory motor stuff, I don't have a good example for that yet. It's going to be somehow in goal-oriented behavior, somehow, I don't know what it is yet, but every time we haven't spent a lot of time, but every time I do spend on it, I find myself going down lots of different directions. And that tells me we don't have enough of a clear problem statement. But I'd rather the problem statement be not like solving a hard application, but having a set of technical requirements that I know it has to do this, it has to do like, I could say, I know it has to have an exploratory learning phase. I know it has to present multiple options. I know it has to be able to, in real time, adjust its behavior based on sensory input. So it may have a chosen path of action, but it can continually adjust every moment in time. I understand that part, by the way. So it's something along those lines, but I don't have it yet, Rick. So it's sort of an organic process where you go through it and all of a sudden it becomes clear, like, this is a really good problem statement.
Okay. I don't know whether I can contribute something in terms of abstract constraints. I would have thought that the constraints you had for, it has to do this, has to do that, were already enough to narrow down. I have maybe a sample application that could help, frame the mind. I dabble a bit in the community, academic community of agent research, agent research.
Agent.
And sorry?
Agent research?
Agent research?
Yes. So one interesting thing I saw that conceptually is relatively easy for two agents, as they call them, to develop a language between them. Language in the very abstract sense, not English. So that the internal representations that they have, which differ for common external phenomena that they both observe, so that they get aligned and that they can communicate about them. And I can post maybe a link to a paper here in the comment section of the talk here, so you can click that. So basically you feed the motor actions of one agent or HTM in this case. We feed the output of one into the input of the other, and vice versa. And by learning coincidences and coincidences of sequences of these things, they develop common internal representations. And if you can get that working, that opens the door to all sorts of other things. You can dramatically increase the scope of any application that you have by just employing multiple HTMs that are very loosely coupled, not tightly coupled as to form a single HTM, but very loosely coupled. And again, there are lots of interesting problems that can be solved with that. So if you can get, yes.
Are these two separate agents? Like, are we talking about two parts of a similar network, or are these two separate HTMs, two separate organisms? What are we talking?
Two separate organisms. Two separate organisms. Yeah.
Why would you want to go to that complexity to get? That seems like it's surprising to me that you'd want to go there initially. Like, I would think, if I think, like, why can't I have a single HTM that sort of is living in some static world? Imagine like a rat in a maze, or a person walking through a house, and you want to learn goal-oriented behavior. I just want to, like, how do I get from point A to point B in the most efficient way, or how do I solve a particular problem? I don't need two agents to do that. Why would you want to go to two agents to begin with?
The goal first would be to develop goal-seeking and sensory motor integration to a point that two agents can develop a language between them in the first place. Yeah.
That seems very complicated. Why wouldn't we start with one agent?
Well, one agent cannot talk to themselves, really, right? So that doesn't make much sense.
But one agent could learn goal-oriented behavior. You don't need two agents to learn goal-oriented behavior.
the goal is just that they communicate with one another.
Okay, well,
Right?
that's a different task, right? I mean, I guess I'm having trouble combining that with goal-oriented behavior. Why, developing a language that communicates is pretty cool, but that doesn't seem the heart of goal-oriented behavior. That seems like a different problem, unless I'm missing something.
Sorry, maybe I went rushed too far, but so one agent's goals is that I need to communicate this situation to the other agent, and so I have to string together these words, and these words strung together are the steps to achieve the goal, and so that's the simple thing, right? I'm forming a goal in my mind, I have to convey something to you now, and I'm stringing together a few words which are the motor actions. So that's...
Hey, Rick, let me try, sorry to keep interrupting you, but here's one way to think about it that might combine these two things together. The way I view it is the cortex sends a behavioral signal, and it doesn't really know, a region of the cortex doesn't know who's receiving it and what its effects are. All it can do is it can sense what sensory changes have occurred. And it doesn't know if that sensory changes occurred because it moved its arm or because something else in the world was impacted. So the way I view language, for example, it's just an extension of that. It's saying, okay, I'm generating behavior, and I have to learn what results from my behavior. That behavior could be language operating on another agent, or that behavior could be myself operating on my own body, or that could be manipulating some inanimate object in the world. But in the end result, is all I know is I've sent a behavioral signal, and I've learned what to expect in my sensory change. And so this is a very nice idea in that you can say, I can understand all things, interactions in the world under the same umbrella. I can say language is really just, language in its effect on other people is just an extension of the basic idea that I generate some behavior and it has some effect. And we try to learn which is the most effective behaviors to achieve certain goals. So I could argue that language is really not a special case. It's just an extension of the basic case. That's how I've always thought about it. Does that mean?
Oh, absolutely.
So then, why wouldn't I want to pick the simplest example of a problem where I have some effect on the world, but I don't know exactly what it's going to be, but I have to learn what it is. And that seems simpler to do that with an inanimate object than with an agent.
Okay, from what I've seen demonstrated by people who are into this, it didn't seem very complicated, and it seemed, yes, it's arbitrary and it's not a special case. It's just a sample of the general case, and but it seemed simple enough to use as a sample, and not more complicated than the mouse in the maze or any of those.
You think I thought it's more complicated. Because I have another agent who's learning, and if the other agent's learning, it's kind of hard to control the experiment a bit. But look, we can just, there's no right answer to this question. I'm just giving my opinions about it. Say connection loss is still connected.
That was my mouse.
Oh.
Okay.
But look, I don't want to discourage it. I mean, it's an interesting idea. I wouldn't want to discourage anyone from working on it. It just seems to me that you're adding a complexity that I would want to have a simpler problem than that. It seems to me learning behaviors in a maze, for example, is a simpler problem than trying to learn to control another entity that's changing and learning as you go. I don't know what else is about that.
I agree. That makes sense.
Okay.
Go for it. Moonshot. Just. It's just like we were talking about the continuous learning thing. I don't want to discourage anyone from doing work on these things. I guess we're a bit more careful here. We're trying to learn that if you try to tackle too much at once, it can really get pretty hard.
Okay, I can't make a statement as to how complicated it is, but it's probably more simple than it initially seems.
Well, maybe you could define, if you could define it in a very concrete example, what these agents are, what you want to communicate between them, what tasks they're trying to solve, a very, very precise problem statement. That would be helpful.
I mean, the other issue, though, is if you're trying to do something so complicated, it's hard to get inspiration from neuroscience because we don't really have that much detailed knowledge at that high level.
Yeah.
And it's much easier to get knowledge at sort of lower levels and simpler things. So that's where all the nerves, and if it's the same principles for doing both, at least there's more data that you can work with the simpler
I
things.
think the broader case, it's becoming very clear to me, the broader thing I would want to start with is I'd want to start with an agent that's learning goal-oriented behavior in a world that is I wouldn't say static, but it's not, its dynamics are not changing. So it's a world that can have objects and things moving in it, but I don't want the world to be learning at the same time. That seems to add a complexity which makes it very hard for me to deal with at the moment. I prefer to say, okay, it's a static world or a world that has, it behaves the same way all the time. And then I think the simplest world which implements the goal-oriented behavior. To me, the problem I'm stuck on here is how is it that Cortex generates multiple, I'm so stuck on how the Cortex generates multiple goal-oriented behaviors at the same time and how we would then select from that. Actually, it's not in the form, it's really just how does layer 5, in my mind, I have a current state of the system, yet it has to create a union of possible behaviors. And evaluating the benefit of them is not the hard part. It's actually creating the union of these possible behaviors. That's the part I'm stuck on right now, which I think I don't believe what happens. So.
Okay.
Thank you, Rick. I'm going to move on to Ryan, but first, if there are some people viewing this, if anybody has any questions, you can ask them through the Q&A interface. So let's talk to Ryan James McCall. Hello, Ryan.
Hello, can you hear me, guys?
We can.
Very well.
Thank you very much for hosting today. I guess I'll start on the motor stuff. So I saw on your blog that your intern, Yue, I believe is his name, he had some work posted there about a simple agent which could move in a multicolored tile world. And so that was an interesting first example, and I wondered what sort of domains you had tried out in addition to that, or if you're still working in that domain.
Which one do you guys see now?
You want to explain the experiments that we have in NuPIC research now?
Yeah.
Sensory motor.
Sure. Yeah. So the first experiment we're doing is to try to understand the capacity of the sensory motor inference layer to learn the sensory motor sequences. So we started with an abstract world, which is the 1D world of letters, and it could move around laterally in the world and basically jump between letters. And so the goal was to have it move around, and by moving around, it's generating a sensory motor sequence, because it's the sensor that's reading the letter, and the motor value is the motor command is the jump to the next letter. So to see whether it could learn to predict all the motion, all of the sensory input due to random motions in these worlds. So we did experiments with different sized worlds, so different number of letters in a given world, and different numbers of worlds that it has to build a stable and unique representation for each. And so a lot of the experiments in NuPIC research are there that basically tests when it starts getting confused between the worlds, whether it can form a stable representation for all the worlds for different sizes, increasing these numbers. And that is more like an experimental.
Yeah, that's essentially the same experiment,
yeah.
except we're not using colors to.
Yeah.
And
These
it's
are
more of a
conceptually
test.
These are all topologically, that's not the right word. But
There's no topology.
No. I was going to say, these are all essentially the same problem as creating a stable representation during eye movement of a visual image.
Right. Yeah.
But they're all equivalent. It's just that you can make very, very simple versions of it. I just want to point out that that's what we have in mind when we're doing these experiments. We're not using letters, and we're basically what's the simplest version of a vision experiment where we're capturing the essence of the problem. And then a lot of the effort's been on trying to figure out the capacity of the system to do this, because it seems like the capacity is going to be the challenge. So we're trying to understand that.
the goal of this is to take this simple and clear system and move it towards more of a vision kind of task, not to do vision, but just to, not for the sake of vision as an application, but to basically see how saccading over an image would form a stable representation. So we're also building scaffolding for doing like try to build stable representations for images of handwritten digits, for example, which is just one example.
So can I jump in, ask a question?
Yeah.
So you're thinking of a matrix of pixels for a letter, and you do the same kind of random movements throughout that image?
Yeah, exactly. You could think of as a matrix of, an image basically as another static world that you can saccade around and build up a stable representation for it. And if you show a different image or a different static world, you should have a very different representation for it, but still stable as you saccade around it.
And so there's the fovea, or how do you model that?
The initial ones will be very simple. It won't be a real model of a fovea. It'll just be looking at different parts of the image and saccading around it.
So a lot of people, I think, get confused by this, because when you think about vision, you think about the fovea and the retina, you get the sense that every time you move your eyes, you're sort of shifting the pattern. It's not really true. It's just a totally new pattern coming into the retina, or coming on the optic nerve. And for every eye movement, even the smallest of eye movements, microsaccades, it completely changes the innervation of the retina. So at this point, you can throw away the idea there's a fovea or anything. It's just like pattern A and pattern B and pattern C. And you can't assume that even for the smallest movement, you have to assume there's no commonality in those patterns. It's just a new pattern. So it makes the problem, in some sense, harder, but that's what the biology says. And it forces you to solve the hard problem is, you can only build invariance a little bit in any particular region and a layer, and then you have to do this in a hierarchy. And so we know that's the case. And so anyway, I'm just saying that thinking about the fovea, it's easy to fall into that trap. I think that's somehow important, but it's not really. It's just like pattern A, pattern B, pattern C at different points, and you're saccading between them.
So I think kind of the next step in this process is to see how we can scale up the experiments. How many patterns can we learn? Can we build up a simple two-level hierarchy and get stability in the context of, let's say, a simple vision experiment? So in terms of kind of day-to-day activities, we've got a Python implementation of the sensory motor inference and a Python implementation of temporal pooling. Those implementations are too slow for us right now. So Chetan's been implementing a C++ data structure that will help speed up those experiments. And so as soon as that's up and running, which should be pretty soon, I think we'll be able to then do another, more scaled up experiments on that.
What's the dimensionality of the inputs you're working with?
Initially, we'll probably do something like MNIST size, which is about 28 by 28, but try to do a simple two-level hierarchy there.
Cool, it sounds really neat.
Thanks, James.
Ryan.
Ryan James. Thanks, Ryan James. Okay.
Oh, one other quick thing, Ryan. I think it was another Ryan. This is confusing. Ryan McCall posted a question related to. Oh.
Yeah.
James.
Ryan James.
Oh, right. You're Ryan James McCall. Okay. Okay, so you had posted a question about details of the algorithms and stuff, and if you actually look at the NuPIC research wiki page, there's sort of simple verbal descriptions of the algorithms. Maybe Matt, you could.
Yeah. So this is question number 2, and we've got NuPIC research wiki.
Yeah. So it's not a very full-fledged wiki, as you can see, but if you go to occasional meeting notes,
that's the first place I'd go.
Go to the October 23rd link. Chetan did a nice job of sort of describing the overall proposal and some of the issues and working through some simple examples. If you go down a little bit, there's a description of the sensory motor inference one, and then a description of the temporal pooling algorithm. So you can look at kind of the actual, a sort of a high-level description of kind of the algorithm that we're working through right now. We're pretty happy with this algorithm at small scales. It's really a scaling issue right now that we're dealing with.
Yeah. And for that, we're experimenting to test the capacity, because that will drive further theory research on it.
We don't know yet whether we'll have to do something different to scale up or not. We might, but as soon as I said, it's kind of working nice on small problems. At least it's doing what we want to do and using the methods. And the real question is, can you really get this to work in a hierarchy in a big way?
Yeah.
Okay. We have not gotten any Q&A questions, so we can probably go and see what other.
Can I just go back to the earlier question? I think it was.
Sure.
Well, while you're doing this, maybe it was Rick's question, but what's a good problem statement? I just want to recognize that I mentioned this before, but I'll say it again. It was, when you think about vision, you say, oh, I should recognize something, and that's the first thing that people want to do. But in the end, we decided the right problem statement was not to recognize something, but to create stability, even though you're moving. And it was just, a little counterintuitive at first, but we think that actually gets closer to the difficult part, and to create stability with eye movement.
Yeah.
Where like almost no other vision systems have that, or no deep learning vision systems have that. Nothing like that at all. We think that's the crux of the problem. So, just again, I think it's kind of what makes a good problem statement.
Also, because it's not vision that we're really interested in; it's sensory motor.
Yeah, it's sensory motor.
That's a good point. I mean, that's problem statement applies to any sensory modality. It's not just vision.
So we wouldn't want something that fits only for vision.
Yeah.
Okay, so I'm going to share my screen. Oops, that's the right screen. Okay, so here's the wiki where we were posting questions for today. So the first one, this is from David Ray. Do you feel that any elements within NuPIC research are becoming concrete, as in likely to show up in the version release in NuPIC, or any concepts becoming concrete? That's.
So I'm kind of answered this one a little bit, right?
Yeah.
We're making decent progress on layer 4 sensory motor inference. I don't know what the answer to the question. What does this show up in release NuPIC? I have no idea.
Well, how maybe what's the process of getting the work in NuPIC research into NuPIC? When some of this is already
happening. For one, there's the optimized C++ data structure that future algorithms of HTML learning algorithms are going to use. I just merged that to NuPIC core today, and a temporal memory implementation that's faster, functionally the same but faster using the C++ data structure. I should be merging that very soon. So in terms of like optimizing and improving the algorithms, that is in progress, merging into NuPIC. And then we'll also probably do a temporal pooling implementation that uses that. That'll be faster and simpler than the one that we're currently using in NuPIC research. The one that we're currently using in NuPIC research is slow, and so we would do one that is faster. So in terms of what is being merged currently, it would be optimized algorithms.
Yeah, in terms of what is the process for moving new things in, I think that's really more up to the NuPIC community than us. Right now, I feel like from our side, from the research standpoint, we just want to be able to move really fast. So I don't want to worry about, I feel like there's a higher kind of standard of what's merged into NuPIC than what's merged into NuPIC research. NuPIC research, we can just push as we want, we can break things, we're free to do whatever we want. We're not hiding anything, but the speed of research is much faster right now. I think once we feel when that's becoming more stable, slower, that might be the right time to move things into NuPIC. But the community can do whatever they want. They're both open. You can do a pull request if you want. And
this is the community member experimenting with stuff.
Yeah.
And they might do it outside of NuPIC for a while, and if it gets stable and we want it NuPIC, we'll merge it.
Right.
Yeah, just to clarify, the NuPIC research repo is not a fork of NuPIC. It's extra code kind of on top of
it's on top of
it depends on NuPIC. So the infrastructure of NuPIC means that you can swap components out, provide your own algorithms in places, and that's how it's working.
Yeah.
The separate question, but maybe related, is I think about when would this be useful for something.
I think that's the question.
And in the end, I actually think, well, we might be doing something in vision, but I actually don't think its first utility would be in vision. I think its first utility would be in something else, which is still not sure exactly what it is yet, but I have some ideas. But I love to productize this. I love to turn this into something practical. And my idea there is that it's a general way of discovering structure in static patterns, static data. And it's discovering the structure and doing inference on complex spatial patterns. And then you can apply that to a lot of things, not just vision things. So in the back of my mind, I'm looking like, well, when could we turn this into something really useful? And I got a couple ideas about that, but it's a little too early. That's independent. I don't know when that gets released to anybody. I don't know.
A question from David Ray that's along this same lines with NuPIC research is when will that data structure that you're referring to be duplicated in Python to make it easier to port? He's the one that's been working on the Java port, and is it even necessary? Is my question. Yeah, it's just for C. It's a C++ optimization.
So it's a data structure that's designed to enable Python code to use as well. So it just manages connections and computing the active overlap at segments really fast, computing predicted cells really fast, and so on. And so that is a basic core data structure that can be used by Python and by C++ code as well. I think your previous version you have something like it in Python, but not the exact same thing.
Yeah.
The whole point here is to have an optimized data structure, so I don't think we're planning to port it to Python.
Yeah.
Right. So you might have to read some C++ data.
Yeah, on the other hand, I think Chayton did a really nice job. It's very simple and clean. It's not that hard to understand.
Yeah.
The Python version is still better though.
Yeah, but it's different. It's a little different.
I thought you were saying that.
It's similar conceptually. The actual implementation is slightly different.
But it's not identical.
It's not identical. That's
Because we're trying to optimize. And so the first Python version I think was like clean, conceptual, and the next one was like, how do I get this to work really fast? The C++.
Yeah.
And so I'm guessing you're doing some data tricks or
Right.
But yeah, I think the really good thing is we've come up with an abstraction that we can optimize and put in C++ and keep the Python code to minimal and experimental, and that way we don't have to maintain too much duplicate stuff between Python and C++. Whereas in the past, there was a lot more that we had to maintain. By coming up with this abstraction, we can minimize the amount that we need to duplicate.
So you think you should be copying that C++ data structure in the Java code?
Yes, but recognize that it's very new and it might change, so.
Yeah.
But you're about to check it in?
You did this morning.
Must be done.
Yes. It might change as we optimize.
Yeah, the next step for it would be to make it faster. But I don't think, not anytime soon is it going to conceptually change drastically. But the implementation might change a bit to be faster.
Okay. Getting a few more Q&A questions. This is from Felix Andrews. He was the author of the closure report on Vortex. Says, how important is the choice of saccades, assuming saccades are not random? Choice of saccades.
The choice of,
so
like the saliency map and so on. How important is choosing a good set of saccades?
Well, we're starting with the assumption that you don't choose the set of saccades. That's the harder problem. Like, we just make random motions. And that's the more difficult problem. Obviously, we do know that saccades are not very precise. You don't do the same ones over and over again. They tend to focus on certain parts of an image, but not exclusively, and they don't repeat. So nature seems to be somewhere in between, like picking perfect saccade or fixation points and being random. The random is the harder case, so we're starting there. If we can get it to work in the random case, then anything that is better than random with a saliency map or something like that will make the situation work better.
Just train faster.
It'll train faster, or maybe able to train more than pure random.
So we're assuming it's basically an efficiency issue.
Yes.
Optimization.
At the moment, we're assuming that way, right? So we're going to push the limits of random saccades and see where we go and how well it works. And it's not too far from, it's, I think I explained it, it's not really crazy, because there's a lot of randomness or unpredictability in real saccades. But it's somewhere in the middle.
So we'll figure it out as we go.
Yeah, but again, pick the harder problem first, and then characterize it, see what the limits are. And again, the whole idea of a saliency map, which is the term they use often for this, may or may not apply in other domains. If you're trying to make something that navigates through some data structure, that may not apply somewhere else. So let's not focus on something we know that's vision only. And if we can get to work with random saccades pretty well, then anything you do makes the job easier is great.
Okay, great. Next question's from Bradley Frank. I chat with him on IRC all the time. He's ADOS there. Can you talk a bit more about how to determine if swarming is finding a good model for the data? I see a mention of an error score. What does that actually represent? That's a good question. I couldn't answer him on IRC.
Oh, okay.
I couldn't.
Oh, you couldn't. Oh, okay. Yeah, you can answer. So we have a number of different error metrics in there, and we basically optimize what swarming is doing is optimizing that error metric. So I think the default is MAPI.
Just to step back, this isn't the OPF, so you have to specify a field as a predicted field,
right?
In any swarm. So one of your fields is being predicted, and the error metric is computed on that.
Yeah. So the lower that error is, the better the model is doing on swarming. The better the swarm model is, and
the better it's predicting that value.
The better it's predicting that value. Yeah.
Over the history.
Over the history. It's a windowed moving average, and by default, I think it's looking at the last 1,000 records. And it's important to remember, I think, that the error is calculated before you train on that data. So there was a question somewhere, I think, about splitting up data into training and test sets and stuff. You don't need to do that in the OPF in a streaming context. So the system is making a prediction about the next step. We calculate an error, then we show the system that next step, and it adjusts itself. So it's actually a correct way of doing not fitting to the training set. I don't know if that was clear, but
sure.
There's a question always, if you train on the test set, then you're basically that's a cheat. You're not computing your error correctly. But this way of doing it, and this is sort of a well-known way of doing it in time series in general, it does not have that problem. You're always making your prediction and calculating the error before you actually train on that record.
We don't cheat. We don't look ahead.
We don't look ahead. The system doesn't look ahead.
You should wait to see what the value is to compute the error, but the prediction that you're using is from before you ever saw it.
Exactly, yes.
So there's always a little confusion about this, especially since we're doing a lot more anomaly detection stuff. And I've had this conversation with a lot of different people. When you swarm for something like Sutai and Scott said, you're swarming for the accuracy of a predicted field that's defined in the swarm description. You may not get the best a model for anomaly scores doing a swarm for a specific predicted field.
But it's a good guess you would.
Yeah.
Right. I mean,
it's a good starting point.
Building a better. I mean, the whole anomaly detection is based on the idea you have a predictive model.
Mm-hmm.
If you don't have a predictive model, you can't do anomaly detection. So presumably, the better your predictive model is, then the easier it is to find deviations from it.
It's pretty much impossible for you to prove that it's not the ideal model, really.
Well, it's probably difficult to prove that it is the ideal model. But
so I've been in this situation where I didn't realize this before, and I swarmed over something to get a model that I changed into a temporal anomaly model. And then after talking to others in Sutai, I found the anomaly parameters we use within like Grok for CPU stuff worked better than, for me, trying to get anomaly indications out of the data than did the model I got back.
Those are hand-tuned.
Those are hand-tuned specifically for scalar anomalies.
Yeah.
And
well, we don't swarm over those data sets, right?
No, but so I actually had some situations where I could prove what you said couldn't be proven. So, so you can prove that I have situations where the best, the model with the lowest prediction error is not the best for anomaly scores. And the reason for that is that the measure, the error measure we use just uses the most likely prediction and calculates error with that, whereas what the system is actually doing is making multiple predictions, and anomaly score is computed with respect to that. So you can come up with scenarios where picking the best single prediction is not the optimal model. And for minimize, yeah. And so on the other, so that's why this is just an approximation, and the hand-tuned model is actually better. On the other hand, that sort of begs the question: what should you optimize for anomaly score?
Optimize for a labeled data set.
Yeah, so we don't have a good metric for optimizing for anomaly scores. If you just optimize on the anomaly score itself, you can easily come up with a degenerate model that just says everything is predicted, and therefore the anomaly score is 0 all the time, and that's not going to be the best for anomaly score. Yeah.
Optimize on the error of detecting an anomaly. You have a labeled anomaly.
Yeah, but that requires, that's not a generic error metric. You need a labeled data set.
Yes.
And that's really hard with anomaly.
Doing a labeled data set.
Yeah.
That would be the most direct measure of error on
yes. But for prediction, you can just feed it a stream and get a decent.
Assuming that someone could create a labeled data set, could someone, I mean, is it theoretically possible to create a swarming process that optimizes for anomaly detection?
Yes.
You need a lot of data, though.
You need a lot of data, and that's a great reason why we're doing NAB.
Yeah.
Just a labeled anomaly benchmark that we could actually optimize against.
Right. We haven't really talked a whole lot about NAB. I'm wondering if I should just at least show it for the people since we mentioned it that are watching. So we have this repository called the NuPIC Anomaly Benchmark. It's a work in progress. Yeah, like you can see, under construction. But we're trying to get to a point where we've got all these comparisons of or benchmarks that compare us to other different anomaly detection engines. That's the goal. I don't know exactly where we're at on this, but we're working on it.
It's in progress.
In progress.
It's not our highest priority.
Okay, so we ran out of questions here, but we still have one.
There was yeah, that's right.
That we already talked to Ryan and Rick. The fourth one, which came in this morning.
Oh gosh, I should have done my homework.
This one was put in last minute.
Yeah.
Yeah.
So he's referring to the work that Felix did that he posted on this on the mailing list, which refers to. Let me get this open. And I think he mentioned this at the hackathon. This was right after the hackathon, but he was doing textual work with Portable.io. I didn't have a chance to read this blog post yet, so maybe. And Jeff, you probably didn't either. Maybe this is a bad place.
From what I understand is he's trying to do generalization using just the sequence portion of it. I haven't read it in detail, but he's Cortical.io has they're doing the opposite. They're creating really good SDRs and counting on the SDRs to do a lot of that generalization.
Mm-hmm.
And Felix is kind of exploring what you can do with sequences. So he has.
So he's using Cortical.io.
No, he's using random vectors for the words and seeing what can you get out of the sequences from a generalization standpoint, which I think is an interesting idea.
Mm-hmm.
I don't know. I can't speak to the specifics of his blog post because I haven't read it in detail, but I think that's what he's exploring. So things like, if you say someone has something you've seen has before, even though you don't have any semantics associated with it, maybe you can do some prediction of that. So I think I may be completely misrepresenting.
So
Felix.
This is from Kevin Mendley, and he goes on to say a similar mechanism was suggested a few months ago in the Rob Frieden Fergal burn discussions that were happening, but it didn't get any attention. So he quoted it saying, if cells that are predictive, depolarized, were to be given a competitive advantage toward being activated by the spatial pooler,
yeah, so this is something Fergal has mentioned many times, including last year, and I did reply to that. I don't know if there's been anything new there, but I think this is a decent idea. The basic idea here is that when you're doing spatial pooling, use the predictions from the previous time step in the spatial pooling step as well, because that would actually be available in real neurons.
Yeah.
They're not separated out that way. So I think this could be very helpful in extremely noisy situations where it's really hard to tell from the bottom-up information what the pattern is. But if you've learned sequences, then the temporal predictions could help disambiguate what the bottom-up patterns is. And
We actually know, well,
we did some work along those lines way back when.
Yeah.
We used to call it like time-based inference.
yeah,
And we showed that it does help in really noisy situations. We haven't done it in the context of
no.
the cells and columns, but I think it would be great if someone wanted to prototype it and try it out on something.
So we have no plans on working towards that, but we think it would be an interesting idea.
Yeah, it may come out of also the more recent stuff we're doing, because we're trying to unify a lot of this temporal pooling, spatial pooling, temporal memory, all
A
of this.
related topic is how feedback from
Yeah.
region to region
Yeah.
does this. And I think this is exactly what it's doing, region to region. So, when you feedback from one region down to the April, then you rise to the previous region, this is exactly what's going on. I think this question is more how does it influence the spatial pooler, and I'm not really certain how that.
Yeah, I don't know how that would work in the biology. I think
Yeah.
algorithmically it seems like it could be.
But there wasn't good biological support for the idea of influencing, like layer 3 influencing layer 4, or the inhibitor cells. Doesn't mean it doesn't. It's not there, but I don't know the evidence for that. There's lots of clear evidence from region to region feedback. So, but I believe this proposal is more local.
Yeah.
So
So if someone were interested in working on this, maybe give them a pointer on where they would start in the code base. This is something.
Well, actually, Fergal has emailed something with that, with some very specific proposals, like months and months ago.
The region implementations that we have a notion of top-down out and top-down in that we're not really using right now that you could use that would be for this type of information.
In the network API.
Well, in the regions, the spatial pooler region and the temporal memory regions.
Oh, okay. So
No, that's a good idea. Yeah, you could feed it in that way and just have the spatial pooler and then be biased. Use that as a bias.
You guys use that for something like that.
But this isn't a part of the network API. It's not a part of the links or anything.
It's implemented using the network API.
Yeah,
It's just a convention.
Okay. Hey, it looks like we're out of questions. Let me just check real quick to make sure I didn't miss anything on the
and it's
page.
perfect timing.
It's 3 o'clock.
Yeah, it's like 3 o'clock exactly.
Yeah, we did this 2 times in a row. It's amazing.
All
Good
right,
job, Matt.
folks. Thanks for joining us. I hope you enjoyed spending an hour with the NuPIC team talking about HTM. And hope you have a wonderful week.
Yeah.
Bye.
Bye.